We talked about conditional probability already when we did the example with the 3 doors with 2 goats and a brand new car. When we did the example of when I rolled the dice and said, one of the dice is a 3, what's the probability I rolled a 7? And the answer was 2 11s. So a conditional probability, what it does is it takes our product rule for dependent events, which says what's the probability of A and then B? Well, it's first the probability of A, and then we have this times by the probability of B given that A has happened. So this notation with the B and then the straight line and then the A, that straight line means given. The probability of B given that A has happened. So we can do an example of this given idea, okay? Now, for example, I could say, what's the probability of getting a spade? If you picked out of the cards here. I hope that you would see that it would be 1 out of 4, okay? But if I went and I took out all the diamonds and put them aside, now what's the probability of getting a spade? Is now 1 out of 3, because the diamonds are taken out. So this, what's the probability of a spade on its own would be 1 out of 4. But if I had, what's the probability of a spade given that all the diamonds are taken out, now it's a different probability. So often we have something like this. What's the probability of getting 2 aces in a row? Well, the probability of getting the first ace would be there's 4 aces out of 52 cards. 4 out of 52. So we could easily do, what's the probability of ace and then another ace? Well, the probability of the first ace is 4 out of 52. Then the probability of the second ace is, given that 1 ace is already taken out, it's now going to be 3 out of 51. So this dependent events, when you get an example, it seems quite intuitive, but this is what the notation looks like. Rearranging our product formula, we can get that second part by itself. The probability of B given A is the probability of A and B divided by the probability of A. And how do we know that we're going to be doing a question that involves conditional probability? There's some keywords. Sometimes they say given or if or suppose. And they're telling you some information that is known. And if I give you information, it's going to change your probability. Okay? Some of these given ones you can do intuitively. Okay? Given that I picked a red card, what is the probability I got the king of hearts? Normally the probability of king of hearts would be 1 out of 52, right? But I told you it's a red card. So now the probability is 1 out of 26. Because now you only consider the red cards. So conditional probability will always reduce your total. And if you think about probability as events is like favorable over total, this bottom part of the formula, the probability of A, is, in a sense, reducing your total. Because the probability of A was the idea that was given. Just like when I told you I had a red card, you knew that there's only 26 red cards now. So given information changes the number on the bottom of the fraction. If we go back to that example that I said before, where I said one of the dice was a 3, where is that beautiful dice? There we go. If you know that one of the dice was a 3, that means these are no longer longer options, these are no longer options, these are no longer options, and these are no longer options. By telling you one of the dice is a 3, it reduces your total to only 11. And now if I ask, what's the probability I rolled a 7, it's 2 out of those 11. We're going to do that same question with the formula. Okay? And we're going to look at how we can use the formula to solve a bunch of these questions. There we go. Sometimes we can do these with Venn diagrams. Of 53 staff at a school, 36 drink tea, 18 drink coffee, and 10 drink neither tea or coffee. Can you draw that Venn diagram? Once you're done your Venn diagram, have a look to see if you came up with those numbers. The 10 you could put in right away. When you were figuring out, just a show of hands, did everybody write the 10 first? Yes? Okay. How many people found the 25 next? How many people found the 11 next? Okay. How many people found the 7 second? Okay. So, the typical way for finding the 11 next would be to say, if I do 10 plus 18 plus 36, that adds up to 54, 64. That's 11 more than I was supposed to have. Is that how you found the 11? Added everything up and got 11 too many. But if you add everything up, you would have counted the middle section twice. So that's why it's an 11. Okay? You said you found the 7 first? A 7 after the 10?
Yeah.
So probably, is this what you did? You knew this was 10. You knew that the whole green circle was 36. 36 plus 10 is 46. How many more to make 53? This has to be a 7. And once you have that 7, then you can find the middle, and then you can find the other number after that as well. So there's a couple of options for how you figure this out. Once we have the Venn diagram, our probability questions become easy. Drinks tea, but not coffee. Can you see that tea but not coffee is the green 25? 25 out of the 53 people. Because probability is just how many over the total. If he is a tea drinker, that he drinks coffee as well. This is a conditional probability because a condition was given. We know the person is a tea drinker. So now, with a Venn diagram, we could do this question directly. But our total won't be 53 anymore. Our total on the bottom of the fraction, because we know they're a tea drinker, is going to be 36 on the bottom. Does that make sense? Because you're told they're a tea drinker, your total now is only 36 people that you're thinking about. How many of those 36 drink coffee as well? 11. Now we could do this with the formula. The formula would say this: what's the probability of coffee given tea drinker? And we would have to figure out the probability of coffee and tea drinker, which coffee and tea drinker are 11 out of the 53 people. And then what's the probability of a tea drinker? That's 36 out of the 53 people. And I hope you can see that when you multiply by the reciprocal and that fraction divided by a fraction, you would get 11 on 36 as well. But in this example, I think you knew the total tea drinkers, it would be perfectly fine to not use the formula. But it's nice to see how the formula works. The formula, by putting the probability of t on the bottom, is what reduces that bottom number to 36. We did it directly just by seeing that there was 36 tea drinkers. The conditional probability formula does it with probabilities, but does it in the same way. If he is a tea drinker, he does not drink coffee, so the given part is a tea drinker. Can you see the bottom of your fraction is going to be the 36 again? But not a coffee drinker, well, that's going to be the 25 out of the 36. So some conditional probability questions you will just be able to do using logic. You can see how the original sample space gets smaller, and you can figure it out directly. Okay, card is chosen from a deck of cards. What's the probability it's ace of spade, given that it was a black card? So the fact that you're given that it's a black card is going to reduce it from 52 cards down to 26. How many of those 26 are aces of spades? Just the one. So this would be a great example. If you just wrote down the answer, yes, you could logically figure that out. If you wanted to use the formula, this is what it would look like. Probability of ace of spades given that it was black. What's the probability of ace of spades and black at the same time? There's only one of them out of all 52. Then the probability of the black cards, there's 26 out of the 52. And if you take that fraction, divide by the other fraction, multiply by the reciprocal, you get 1 out of 26 as well. So both of these first two examples were ones where if you drew the Venn diagram or thought about the situation, the condition reduces the total and it's easy to see. Here's an example of one where, just zoom in here for you guys a bit. Here's an example of one where it is not intuitive how things are going to switch. The manufacturer has 3 machines to make kitchen cabinets. Machine 1 produces 40%. It's their fastest machine, makes the most things. Machine 2 does 25%. And then machine 3 does 35%. Now, no matter which machine you use, sometimes it makes mistakes. So machine 1 obviously looks like the best machine. They use it the most, and it only makes mistakes 8% of the time. That still would probably be, if you owned this company, you would be mad at that machine. 8% errors out of a machine is quite a bit. Okay? But machine 2 is even worse. It's 15%. That's the really old machine. And 10%. Okay? Probably a good analogy for teachers would be asking how does the photocopier work? Does it work well? Does it always work? Does it jam? How often does it jam? Right? We used to have an old photocopier that would stop working right away. Right? The newer ones work well at the beginning, and then as they get older, they start making more mistakes. Okay? So you randomly pull a cabinet out, open it up, you don't know where it came from, but you find out it's broken. And you can figure out what are the chances it came from machine 3. And it's not just an easy, it's not 33% chance each. It's not even a 35% chance because there's more defective ones that come out of other machines. So we're going to solve this one with the formula and see how the formula works. And this is a very typical conditional probability where you find something out in the present, like the cabinet is defective, and you want to find the probability of something happening in the past. So the first thing we're going to do with this is draw a tree diagram representing all the possibilities. First of all, it either comes out of machine 1, 2, or 3. So I use the Roman numerals for that. And then after it comes out of machine 1, it's either defective or not defective. So I use D and ND. Sometimes people do B and G, bad and good. You can use whatever letters make sense to the context. Where you can have defective and good. I use D for defective and ND for not defective. So the way that conditional probability works, the fact that we randomly found something to be defective, can you see that that is either here it came out of, here, or here? Those are the three possibilities. Which one it was, we don't know. But we're going to find out what are the chances it came out of this one. So we set up our formula. Probability of machine 3 given defective is equal to probability of machine 3 and defective divided by the probability of it being defective. Machine 3 and defective, that can be represented by this branch. Machine 3 and defective is that branch right there. How do we figure out the probability of a certain branch? Well, probability of machine 3 is 0.35, probability of defective is 0.1, both of them together. We just need to multiply those together. Then the bottom, the probability of defective, comes in 3 different cases. We highlighted those with the yellow arrows. It could either come machine 1 and defective, machine 2 and defective, or machine 3 and defective. And simplifying this, typing it into our calculator, we get just over a 33% chance. Based on what was given to us before. So part B, if the cabinet was not defective, what is the probability it came from machine 1? Oh, that's not what I wanted to do. So we set up the same formula, probability of machine 1 given not defective. Machine 1 and not defective, that I can show machine 1 and not defective by the blue line. And then there's 3 cases for it being not defective, and we would just have to add up all 3. And we happen to get 0.411. Do you know how to use your calculator to switch it back to a fraction? So if you wanted an exact answer, you could find an exact answer, or you could leave the approximation signs with the decimals. Oh, you probably noticed I put your test results in. Okay, we're not getting back our tests today. Yihong still has to write the test. So once he's done, we'll get our test back. Now another way to solve this problem with percentages is choose a relatively large number to hypothesize what would happen. So for example, I chose 10,000 cabinets were made. Does it make sense that machine 1 would make 4,000 of them because they make 40%? Machine 2 would make 2,500, and machine 3 would make 3,500. That would total up to 1,000, 10,000. So I choose a big number, and then I use the percentages that I was given to figure out specific numbers. Because I can now solve these questions. If I make this chart, I can solve this question without a formula. And I'll show you how. First of all, I'm going to put a number 1 beside these ones. Does it make sense that I could figure those out first? Right? Because I'm told that machine 1 makes 40%. 40% of 10,000 is 4,000. Machine 2 makes 25%. 25% of 10,000, 2,500. And 35%, 3,500. Then I could look at the percentages of mistakes. If machine 1 makes 8% mistakes, and I go to the 4,000, 8% is 320. 92% then is 3,680. Machine 2, 15%. Machine 3, 10%. This one's really easy to do the math. 10% of 3,500, 350, means that 3,150 were good. And if we look at the totals, this tells us if you make 10,000 cabinets, just over 1,000 will be defective. And what was our first question? Our first question was, if it's defective, find the probability it came out of machine 3. So using the chart, I'm told it's defective. What's my total going to be out of? 1,045. That's my condition. It reduced how many I'm looking at. Then what's the probability? If I know it was defective, what's the probability it came from machine 3? Well, how many defective ones were in machine 3? 350 out of those 1,045. You type that fraction into your calculator, you will get exactly 0.335 ... This one, 736 out of 1791. How could we use the chart to solve that one? We know that it's not defective. According to my chart, there were 8,955 non-defective ones. What's the probability it came from machine 1? Machine 1, 3,680 out of 8,955. Type that into your calculator, or reduce this fraction, you will get 736 out of 1791. Why did I choose a big number like 10,000? Well, if you chose 10, for example, small number like 10 would be bad because, well, machine 1 would make 4 of them. Machine 2 would make 2.5 cabinets. And now you're dealing in decimals, and all of a sudden, the concept doesn't seem quite right. So choosing a number big enough so none of my numbers ended up with decimals was my plan. But even if you got decimals, it will still work. That's what the formula does. The formula says, we don't worry about decimals, we can just use percentages to figure out the conditional probability. But I think it makes a lot more sense when you see it in the chart. So most likely that the defective one would come from machine 2.
That kind of made sense since it made the most, but it didn't make that many. It could have been that, oh, do I have the example? What's our next example? Oh, I have an example that I used to do in my grade 12 class, where they take a certain, sometimes they know certain diseases exist in the population. There's certain rare chromosomes that cause problems for you in your life with whatever kind of health issue, okay? And they have an idea that 1% of the population has this rare chromosome. Okay, so that means 1 out of 100 people have this chromosome. And they have a test for the chromosome, right? And they have this test, and they say the test is 95% accurate. And you're like, 95%? I just wrote my stats test. That sounds pretty good, right? 95% on a test, you feel pretty good about that. Okay? So you're feeling, elbows itchy, that's one of the symptoms. And you go in and get the test done. And it comes back that you have this rare chromosome. What are the chances the test is correct? Okay? So, this is a good, because this happens. This is a true medical problem that our society has right now. It happens out there. And the amount of stress that's caused on people for getting misdiagnosed is huge, right? So here we go. 1% is known to have this bad chromosome called BC. Okay? The test is 95% accurate. And you want to find what's the probability you have bad chromosome given you got a positive test for it. This is what we're solving. Well, let's look at we could do the formula, but I like to look at it with the numbers. So let's say 100 people go for the test. I'll make a chart. Totals over here. We've got bad chromosome. Let's see. Bad. There we go. Bad chromosome. We got positive and negative test. We got good chromosome. We got totals down here. 100 people. So if the population says, we know that 1% of the population has this, and your totals are 100, I think I'm going to have to do a bigger number. Let's do 10,000. 10,000 people. How many people would actually have the bad chromosome out of the 10,000? 1% of this would be 100, leaving 9,900 people without this bad chromosome. Okay? We're like, it's a really bad chromosome. Elbow starts to get itchy, and then you lose all ability to do math for the rest. It's most people can't really do this. Okay, it's intense. You're feeling the intensity? Now, bad chromosome person goes to get the test. The test is 95% accurate. So that means that of the bad chromosome people, 95 will get a result that yes, you have the bad chromosome. But 5 of them will be like, no, you just can't do math. I don't know what's wrong with you. 5 of them will be told they're okay, even though they're not okay, because the test is only 95% accurate. Now, the interesting thing is, at 95% accuracy, how many people here will get the wrong result? 5% of this, 445 people will be told, oh, looks like you've got the bad chromosome, when they don't. And the other 9,445 will be okay. So after testing 10,000 people, did I add it up wrong? Four, 5-0, right? My bad. And yeah, this would be 5% would be 450. No, 445. That was great. Where's my math going wrong? I'm not using a calculator. I think that's 445. Yeah, is it not that high? 495? Oh, okay. Yes, there. 490. And then this would be 9,000. More. Oh, yeah. There we go. 9405. Here. Perfect. So, of this, we add this up. 590 people would get told they have the bad chromosome. Of those 590, only 95 truly do have the bad chromosome. So if we look at an example like this, 95 out of 590, 16%. This should go counter to your intuition. Because let's go through the story right from the beginning. We have a story, 1% of the population has this bad chromosome. We have a test to see if you have it, because you're worried, because you're banking everything's going to go to crap, and all your math is going to be bad after this, if you have the bad chromosome. So everybody's like, I should go test it for this. You get the test back. If you are told you have the bad chromosome, the chances of that being actually true are only 16%. Wouldn't your brain, if they told you this test is 95% accurate, if you have a doctor and the doctor is told it's 95% accurate and they get the results, they think the results are also 95% accurate, but they are not. It's interesting, right? It's totally counterintuitive. And it happens all the time in the medical world. They don't understand the mathematics behind it. They think they're telling you something. Okay? Best bet, because it's so low, would be to get tested twice. And I'm telling you that as soon as you're tested twice in a row of this, your chances of getting the bad chromosome twice in a row is possible, and it being wrong twice in a row, but it's very, very small. Anyways, hope you found that part interesting as a way that mathematics can sometimes, hopefully, improve our medical system. Let's see which. My daughter Bryn. I think it was, yes. Bryn? I think it was Bryn. When my wife was pregnant with my daughter Bryn, they did a test, and they saw something on the test, and they gave us that the result of this test is that she's going to have a whole bunch of severe physical issues. It ended up being wrong, same sort of sense like this, okay? But the mental stress that happened because of it, right? As my wife was driving out of the garage, she just decided to back into another car. Because her mind was worried about the results of the test, ended up getting into a minor accident. That didn't hurt anyone, but you can see that there's a huge amount of stress level that comes with that. And that stress level might cause other problems. So if we know mathematically what's going on, maybe that can help the doctor say a better result would be honest. The test results came back, and there's something that we're concerned about. We don't know exactly what it is, so we need to do another test. And then when that other test comes back, now they can be more definitive and say, yes, something is really wrong, or actually, everything looks fine as a result. I don't know, but there's a whole bunch of, this is like a theory of knowledge kind of class today. There's a whole bunch of ethical issues, right? Can the doctors get sued if they don't tell the results right away? But if they know that those results are not that accurate, should they, at what point should you be telling results to a patient? How much certainty should you have before you tell the results? And if you're waiting for too much certainty, then treatments you could have done early might no longer be. Oh, it's complicated. Just don't go to hospital. Don't do that. All right. Toby is a rising star at the school tennis club. He has found that when he gets his first serve in, the probability he wins the point is 75%. When he uses his second serve, the probability is 45%. He is successful at getting his serve in 3 out of 5 occasions, and his second serve 3 out of 4 occasions. Find the probability that the next time it is Toby's turn to serve, that he wins the point. So we can draw a tree diagram representing what could happen. What are you going to start with? Serve number 1. Hope that's logical. You wouldn't start with serve number 2. Serve number 1 is either in or out. The probability that he gets it in is 3 out of 5. The probability that he gets it out then is 2 out of 5. If it goes in, he either wins or loses. His chances of winning is 75%. Chances of losing, 25%. If he serves it out, he gets his second serve. His second serve is either in or out. His chances of getting the second serve in is 3 out of 4. Second serve out is 1 out of 4. If he serves his second one in, his probability of winning is 45%. His probability of losing is 55%. How many of you have no idea about tennis? Okay, couple? In tennis, when you miss your second serve, you don't get a third serve chance. It's not like just keep missing until you find out what goes on. If you miss your second one, you lost. 2 serves missed in a row is an automatic loss. What do we want to find? What is the probability that he plays a point and wins? Notice that this question doesn't have any given stuff involved with it. It's just find the probability that he wins, not a conditional probability formula. Finding the probability that he wins, you look at the tree diagram and you say, either you can win this way, or you can win this way. Those are the 2 ways in my tree diagram that result in wins. So I would think of those as two different cases. Let's slide this way. So probability of winning. Well, the first W was a 0.6 chance, that's 3 on 5, multiplied by 0.75. The second one would be plus 0.4 chance times by 0.75 chance times by a 0.45 chance. Can you see how there's 3 branches to get the win with the second serve? So we can total those up. We can take out our calculator here. 0.6 times 0.75 plus 0.4 times 0.75 times 0.45. .585. So it looks like when Toby goes to serve, he's got about a 60% chance of winning every point, which means when he's serving, he should win that little mini game. So you turn on the TV and Toby is playing, and they're in the middle of a rally, and Toby wins the point. And you want to think back, oh, did he get his first serve in or not? But you missed that part. Well, we can figure out the probability of that. Given that he wins the point, find the probability that the first serve is in. So we want to find probability. How would you? Probably I would probably write this up instead of using like FSI for first serve in, because I'm not sure that if I was telling the teacher, they would know that they knew what FSI was. Sometimes it could be, okay, maybe they could figure that out. Probability of first serve in given, I think a W here, they'll figure out that that stands for win. So this is what we want to find. According to our conditional probability formula, this would be the probability of, oh, now I'm using FSI and win divided by the probability of the win. I always remember that the probability of the given thing goes on the bottom because the information you're given affects your total sample space and makes it smaller. So the information that you're given, making a smaller sample space, is always what goes on the bottom of a probability fraction. So considering this, probability first serve in and win, we knew that that was the top branch, 0.6 times 0.75, and we'd already figured out in part A that the probability of winning was 0.585. So this put into our calculator. Approximation sign, since I'm rounding, 0.76936. Or you could do an exact value if you go to your fraction button on your calculator and change this. It is exactly 10 out of 13. So fairly good chance, when you see him win that point, that he had got his first serve, according to the probability given here. All right, and with that, we are sort of now done the first major part of this unit on probability, how to work with probability. The second major part is probability distributions, which connects the first part to statistics that we've done earlier. Okay? We are going to leave this